Advised by Professor Metin Tanoğlu, my PhD study is my subject of presentation today. I would like to briefly inform you about the Composite Materials Research Center. In this center, we look into the characterization and also the tests of the composite materials. We have a certain machinery for that, dynamic mechanics analysis device, phatic device, electricity conductivity measurement design, machine, and also double screw extruders and plastics injection device, raise and transfer molding machine, hot press, press molding, and also surface preparation machines and hot rolling machines, and so on. I will briefly inform you about the presentation, the agenda of my presentation, and then talk about the carbon fiber composites and the methodology of this study. I will talk about the literature, the purpose of the study and the results, the conclusion. As we know, the carbon fiber composites are used in many engineering practice. And these composites have tropic structure, and they are heterogeneous, and that's why in such composites we may see certain damages and defects. And in that fiber reinforced composite, we may see a fiber breakage or a fiber pull-out or a matrix cracking, as you can see here in C. Or maybe we can see fiber matrix debonding, and also we may see the lamination. This is a separation in between the layers, as we know. And that's why we have fiber reinforced composites and the improvement methodologies for them. We have mechanical approaches like Z pinning and stitching. When it comes to Z pinning, this is applied before curing. This is an ultrasonic device used, and it may be steel or composite. It is a pinning methodology, and this is only used for the pre-pregs, and the structure inside can lead to defects. For example, racing-related defects, or maybe misalignment, or in-plane waviness, or splitting and crimping. And the stitching is used over the industrial sewing machines with high resistant yarns, and the adhesiveness of the resins may give difficulty to the needle of the machine, and such double way direction may damage the fiber, and we may see certain holes on the fiber. And those two methodologies increases high delamination resistance, and in-plane wavings also may seem, and the pressure strength, tensile strength will decrease, and the phatic performance also goes weaker, and the cost of those machines are high, And about the materials, the nano additives, ultrasonic autos are used and they're mixed after the fiber. The composite material is created to manufacture. The nanoparticles are the most commonly used. Carbon nanotubes or polypherical systems. Here we see certain studies on in the literature, different contributions by different scientists. Here, for example, nanosilica usage, and it indicates that the breakage toughness mode has increased in nanosilica. And in PVA nanofibers, for example, they are mixed with epoxy, and mod 1 and mod 2 increases by double, and also the phatic performance increases. But it's also difficult to homogeneously dilute nanofibers in epoxy, and the viscosity of the epoxy increases dramatically with these additives. And in composite manufacturing during infusion, it creates a problem. And the method that we used in that system, before going into that, let me talk briefly about electrospinning. This is a simple electrospinning system. One syringe pump. It feeds the solution continuously. High voltage power source, the needle, and the collector. As the voltage goes bigger, the fibers, the solution, and the Tyler, it has a Tyler cone structure after a certain voltage. Then it creates a jet, and during the flight, the solution evaporates, and we create the nanofibers over the collectors. And in the mid-phase interface, we looked into the usage of thermoplastic nanofibers that are electrospinned. Why? Because they have high volume ratio and surface area, and it increases the interaction with epoxy. And they have high porosity, and it facilitates the flow of the epoxy. And this can be easily integrated to the conventional composite manufacturing methodologies. And rather than being applied to the whole piece, it may be locally or partially applied. And in the literature, there are certain studies about that. For example, PSF. Most of those studies are related with Mod 1 and Mod 2 breakage impact. PSF or nylon 66, nylon 66 PLC in Mod 1 and Mod 2, there are certain increases. And about Bilge and et al., we see that they looked into PSI, GMA, and intensile strength. There was a 19% of increase. And the purpose of this study is to manufacture the PFAS nanofibers with non-toxicity and low costs through electrospinning methodologies, and make sure that they do collect on carbon fibers. And the material used is polyvinyl alcohol. Hydrolysis level is 87.2. Polymerization is 1750. Single directional fiber, carbon fiber, and the weight of it is 325 grams. For electrospinning, we prepared the PVA solution, 15% of it, with 15 grams of polyvinyl alcohol. In hot water bath, the solution was acquired. And then the system, the electrospinning system, the syringe pump. On the collector, you can see the carbon fiber, and we used 5 nozzles for electrospinning. And in that video, you will see the folding process with 5 nozzles. These are the working parameters. The working operating period is 60 minutes. We covered the fiber for 60 minutes, molded it, and to looked into their way. We looked at the nanofiber surface density. The nanofiber layer was peeled, and the pieces were weighed on a sensitive scale. And 1.8% is the additional ratio of weight in the total weight of the fiber, and this is very low. And you can see some images of the manufactured PVA nanofiber and their SEM images. You can see different images, and those are the zoomed in ones. The nanofiber diameter over the SEM images, 100 fiber diameter was taken, and their standard and average deviation figures were identified. And you can see PVA nanofibers, and the average nanofiber diameter is 182 plus minus 30. And in line with the literature in the post-electrospinning period, to increase the stability and the mechanical resistance of the fibers, we kept them waiting for 10 minutes in 150 C. And you can see that they are connected to each other as webs, and we can see it more clearly in the right-hand side picture. And then those fibers were taken, and composite test samples were created with vacuum infusion. Then we manufacture carbon composite, and you can see the interface, the core face. The post-curing was conducted for 12 hours at 80 degrees centigrade. You can see the image here. The test samples and the water cutting. After those, Shimatsu test device was used, and they were in line with the SATM standard. The tests were tensile test, the 3-point bending test, pressure test, impact test, and breakage test. In the tensile test in fiber, there was a 5% of increase in tensile strength. Around a 21% of increase was observed, and these values are in line with the literature when you compare it to the previous studies. The 3P banding test, we have seen a 37% of increase, and in spinning strength, there was almost no difference. The press test was vertical and horizontal to the fiber. As we know, the epoxy is a dominant element. In the horizontal and the parallel one, the increase was 7.61. In the vertical one, in press strength, there was a 35% of increase. And in mode 1 breakage test, there was 12% of decrease. And this is related with the damage mechanisms as well, because the damage mechanism decreases the mode 1 breakage toughness, but it can increase the mode 2 breakage toughness, we think. And here in this, the 12% is tolerable, and with certain additives, nanofibers can be improved. In impact resistance, we have obtained a 10% of increase, positive increase, and the DMA test results states that there was a 5 centigrade degrees of increase, and you can see the tensile test results, and we know the temperatures of curing, and in here the nanofibers and epoxy, we can see the nanofibers and epoxy through the SEM images. And in that image, when we look at from that scale, the plastic deformation of nanofibers are visible after the tensile test, and the surface, the epoxy and its plastic deformation, the hackle formation, and epoxy matrix high deformation is the reason for that, the hackles. And here again, after the press test, you can see the vertical images. The nanofibers are in the epoxy material, and the results of this study can be summarized as such. The PVA nanofibers were collected on the fiber, and certain interface nanofiber reinforcement layers were created. The tensile, spinning, and pressure figures were positive. In the impact resistance, there was an increase. In mode 1, the breakage toughness decreased. And this study was conducted and supported by Izmir High Technology Institute Scientific Research Projects Unit. We would like to thank the Cohort Global and all the other institutions who supported the project, and I would like to thank you for listening. If you have any questions, I'll be happy to answer them.